In this video, I'll talk about the 1,2, and 1,4 additions that the organometallics can do. Now, obviously, remember, it's not only the organometallics that can do 1,2 versus 1,4 additions with unsaturated ketones and aldehydes. The other nucleophiles can also do, but for this video, I'm going to be primarily focused on just the organometallics, which one can do 1,2 versus 1,4. Remember that 1,2 is also called a direct addition, and 1,4 is also called a conjugated addition, and another name for that is an Michael addition. And you would see the Michael addition again with other type of nucleophiles as well that can possibly do a conjugated addition. So what that really means, if I'm looking at a ketone or an aldehyde as an example, and it's an unsaturated one. So I got at the alpha and beta position, I got a carbon-carbon double bond. So where the carbonyl is, that's your reference point, and one carbon away from that, that's an alpha carbon, and that's a beta carbon. And on the left side, you still have an alpha carbon as well. But we have a conjugated ketone in this particular case, and I could have a conjugated aldehyde as well. And one of the things that you would see here is I do have a carbon within a positive charge and an oxygen within a partial negative charge. So if I have a nucleophile, I can have that nucleophile attacking this particular carbon here and then protonating that oxygen. So that would have been like adding two things right next to one another, and that's what's called a 1,2 addition. And I'll do an example in a minute. But then if I go ahead and draw the resonance structure of that, the resonance structure of that would look something like this, where I can move this pi bond down here. And when I move this pi bond here, this pi bond will break and you get a negative charge on the oxygen. So at the end of the day, I'll have an O minus there. I would have a double bond here, and I actually have a plus charge here. So technically speaking, I have two possibilities where the nucleophile can attack now. I can have the nucleophile attacking right here, and I can also have a nucleophile attacking right here. So it really depends on the nature of the nucleophile. So if I use the first resonance structure and I say, all right, I'm going to go ahead and use the nucleophile here to do the attack right at that position here. So just kind of keep track of these colors there. And then eventually I want to go ahead and protonate that oxygen. So what I'm really doing in this particular case is adding the nucleophile and eventually protonating that oxygen. So I don't want to show that step, but remember I'm going to be protonating that oxygen here. That would have been called in a 1,2 addition, because those things that are being added, they are right next to one another. So that's in a 1,2 addition or in a direct addition. But if I use a nucleophile that is actually a little bit more selective and rather goes to this carbon here, then I'll end up getting in a product eventually. And it's not going to be exactly the same product. It would have a little bit of modifications, but you can kind of see the big picture there. So I add the nucleophile here, and eventually I'm going to go ahead and protonate. Don't forget to protonate this oxygen here. So I'm going to go ahead and protonate that oxygen, just like I was protonating that oxygen there. So now, if I want to talk about where the things are being added relative to one another, I can call this to be 1, 2, 3, and 4. So they're kind of added on the first and the fourth position. Now you may not see it at the end of the day being added at the first and the fourth position, but in the beginning that's how it's being added. So that's why it's called in a 1,4 addition or in a conjugated addition, and another name for that is in a Michael addition. So the question is, what type of nucleophiles can do the 1,4 additions and which ones do 1,2 addition? Typically, the 1,2 addition is done by something that are very reactive nucleophiles or very strong. So and then typical case being CH3Li organolithium, and the Grignards can also do. Grignard can also do a little bit of a 1,4, but primarily it's just going to be that one, the 1,2 being the major, even though it can do a little bit of a 1,4 as well, but that 1,2 is still going to be the major. The other ones are like OH minus, the OCH3 minus. So I'm not going to talk about those yet. I'm only going to be talking about the organometallics here. The one that can actually do an a 1,4 addition is your organocuprate. So that's the important thing you would have in here because it's not reactive. So you want to, in order to do an a 1,4 addition, I want to use a nucleophile that's kind of relatively stable. So it's not very reactive, but it's still in a nucleophile and it's relatively stable. So the organocuprate is one of them that can do 1,4 addition. Now this is not the only nucleophile that can do an 1,4 addition. You would have other nucleophiles like, I can talk about generically if I say if you have two carbonyls and a negative charge in there, that's also a good Michael donor, just like organocuprate. The sulfur with a negative charge is a good Michael donor, technically. So those are the things I'll talk about them later in a different video. But here I just want to primarily talk about the organometallics. So that's really the difference that you got in there. So if I want to look at this example here, and suppose I'm using a CH3 Li. So this is a very strong nucleophile, very reactive. So it's going to go ahead and quickly add on to that carbonyl carbon, and it's going to go ahead and break that bond up here. And then what you get at the end of the day is I have the O minus here. I have a new carbon-carbon bond made here. And then in the second step, I just need to go ahead and work it up with water acid. So in the second step, I'll just have water dilute acid just to protonate that oxygen. And that's really the end of the story for this 1,2 addition. But then if I was using something, let's say, I'm just going to go ahead and use probably the same guy, but then I'll use, instead of organolithium, I'll use organocuprate. So something like CH3 Li here. So you remember, you're not only limited to those type of organometallics. You can have any R groups here. CuLi. Now this one is a little bit more stable than the organolithium. So as a result, it's going to attack this particular carbon, and then this pi bond is going to come down here, and you're going to have this coming up here. And what I get at the end of the day, let's reform that here. I get an O minus, just like I would expect. I had reformed the double bond here now, and I got the methyl attached here. And then in the second step, I can go ahead and do the water acid workup here. And when you do that, you'll go ahead and protonate this oxygen. So that's why it's in a 1,4 addition, because you can see how the things are being added at the first and the fourth position there. But this one, if you recall this particular function group, it's actually an enol. The enols typically are not stable unless it's like in a phenol. So as a result, you may ended up getting an rearrangements there where it can tautomerize to an keto form. So what I can have here is, remember this is in a 1,4 addition, but I'm not going to be leaving it like that because the enol is not that stable. So instead, I'm going to be going ahead and using the acid here, the dilute acid I have here, to kind of reform that ketone here. So I'm going to go ahead and reform this bond, make a double bond here. I'm going to go ahead and grab this proton from here using that pi bond. So I killed the pi bond here and reformed the pi bond between the carbon and oxygen there. So this carbon would get an extra hydrogen from that water, so I don't want to draw that. and then I would have a pi bond formed right here, and this oxygen gets a positive charge, and then eventually want to go ahead and deprotonate that, and I can just use water because I'm doing this in dilute acid, and this reforms that pi bond. So at the end of the day, it may not look like it's in a 1,4 addition, but it kind of goes through that process. So that's something you want to kind of keep in mind, that what's really the mechanism. So instead of memorizing things, you want to kind of see what's really happening mechanistically. What do you need to memorize at the end of the day is you want to make sure you know, like, okay, what possible nucleophiles can do 1,2 addition versus 1,4 additions. And right now we're just comparing the organometallics. Now, if I was using, let's suppose, um, an organo, a Grignard, so we know what happened with the lithium, we know what happened with the cuprate. With the Grignard, it can actually do both. And even though it does kind of do both at the end of the day, um, it still ends up making 1,2 as your major product. So you may not even, some books may not even have this being written down as both, just because um, I'm not gonna do the actually mechanism here. So just kind of show you that I was gonna do both of them here. So an OH there, got the methyl group attached here, and then the second one would be, should do this copy here. So in case of second one, I would have it after following up the mechanism doing 1,4 addition. I'll reform that ketone from the enol, but I would have that methyl attached here now. So that's really um, the difference here. But even though it can technically do both of them, your major still tends to be the 1,2 addition. So in a lot of cases, if they're asking you only one of the products, you still ended up trying the 1,2. And that's really because of the reactivity differences. The Grignard is a little bit less reactive than the organolithium. So organolithium primarily does 1,2 addition, and organic cuprate does primarily 1,4 addition or Michael addition. But then when it comes down to Grignard, it does have a potential to do both of them. But even though it leans more toward the 1,2 addition is the major product.